Hi friends, in a previous video we talked about bivariate correlation, which is a way of trying to quantify an association or a relationship between two variables. In this video we're going to expand on that. Here's a scatter plot like from before. We can see just by looking at it that there's a positive trend or relationship between x and y. And when we were talking about bivariate correlations, we recognized that we can describe this relationship with a number. It's called the correlation coefficient. In this case, it's 0.5. But what if you wanted to do something more complicated? What if you wanted to see how y is related not just to x, but also to z and maybe p and q and r? Well, if these variables are related to each other, if you looked at those bivariate correlations and there's some sort of trend there, then each one of those might appear to be related to y because they're related to something else, which is itself related to y. Just to ground this kind of abstract idea in a more concrete example, imagine you're inspired by a recent New York Times article and you want to look at the relationship between SAT scores and college GPA. Basically, you want to know, does this test predict success in college? Imagine you're on an admissions committee and you want to know, how successful is this candidate student going to be at our school? Well, you could look at the SAT scores as a predictor of success. But even if the student didn't take the SAT, you could also look at their high school GPA. And their high school GPA is surely going to be correlated with their SAT score. It's probably also going to be correlated with their college GPA. But if you already know high school GPA, does knowing SAT scores help you to make a more accurate prediction about the student's success in college? Right? In other words, does the SAT have added predictive power above and beyond high school GPA? Well, to investigate a question like this, you'd need to move beyond bivariate correlations. You'd need to use a regression analysis. In a regression, you have one dependent variable, but you can have many independent variables or predictors. You can also do fancy things like test for interactions between the independent variables, such that maybe one predictor moderates the relationship between another predictor and the dependent variable. For now, let's stick with a simple case like this one where we have just x and just y, and let's think about how a regression model would work, and maybe we can build up a little bit. In a regression, you have one dependent variable, and you represent the relationship between the independent variables and that dependent variable with a line. Like that. I mean, if we're just eyeballing it, that looks about right. Yeah? Maybe the line ought to be more like that, or something like this, somewhere in here. We can kind of wiggle and jiggle the line and try and see. But in the 1800s, when this kind of thing was invented, that's actually what they did. They'd just draw a line and they'd say, that looks about right. But along come some other people who are more statistically minded, and they said, we can do a little better than that. We can come up with a mathematically rigorous criterion for determining which line is going to fit these data best. There are actually a few different ways of doing that, and if you're interested in that kind of thing, there's a wonderful video on the Khan Academy that will walk you through one of the earlier or more simple ways of doing that. But for now, the key thing you need to know is that a regression line is defined by an intercept and a slope. Or if you have multiple predictors, then it'll be a set of slopes, but we'll get to that in a moment. The intercept is the point where the line intersects the y-axis. That is, when x equals 0, where does the line fall on the y-axis? In this case, it's 0. The slope is comparable to the correlation coefficient that we talked about in a previous video. And we calculate that in the same way that we would have done in middle school math. It's the rise over the run. Slope equals rise over run. So in this case, it's 0.5 over 1.5. That's the coefficient. That's the slope. So another way of thinking about what this means is that the intercept gives you a prediction for what y would be when x equals 0. And then the slope for x tells you how to adjust that prediction given a change in x. So when you have a 1 unit increase in x, how does that influence what you should predict for the value of y? That's actually how a regression coefficient is usually defined. It's the expected change in the value of y given a 1 unit change in the predictor. So here we would represent this mathematically by saying our prediction for y equals the intercept value, which in this case is 0, so that makes it easy. That just disappears. And then we have the coefficient times the value of x. So the slope plus the intercept tells you this predicted value of y. And now we've been focusing on a relatively simple case where there's just one predictor. But again, the beauty and the power of regression is that you can have lots of predictors. So what happens then? what happens when we have another predictor in our model? Well, we just add a dimension to our data. This two-dimensional scatter plot is representing two columns of data. So if we add a third column, then to visually represent it, we actually would need a 3D scatter plot. This is a three-dimensional scatter plot where you can see we still have the x and y axes, but we now have this third axis, z. And if we kind of pivot the camera around, we can see there are relationships between each pair of variables. So x and y are related, but also x and z and y. So we can see there's something going on here that involves multiple variables being related to each other. Now, when we wanted to represent the relationship between x and y, we just had a line, right? And that worked well enough. But now we've added a dimension. So our representation of the relationship also needs to add a dimension. Instead of a line, we now have to imagine that there's a plane in this three-dimensional space. So instead of a string, you could think of it as like a piece of plywood. So here is the same plot, but with that piece of plywood added in, right? You can see the shape of the plywood is going to be kind of raised and lowered. It's going to be tilted and angled in such a way as to try to kind of best capture this relationship between the two predictors and the outcome variable. We can go back to our equation now and think about our way of predicting the value of y. Well, we had this equation where our predicted value of y is a function of that intercept, the value we expect when x equals 0, and then the coefficient for x tells us how to adjust that prediction for a 1 unit change in x. Now, if we wanted to add z to this, suppose the coefficient is 0.2. Now we just know, okay, if we get a 1 unit increase in z, we get a 0.2 increase in y. And the intercept is still basically the same, except it's the expected value of y when all of these predictors are 0. So when x and z are both 0, the intercept tells us what we should expect for y. And then each coefficient tells us how to adjust that. But crucially, because both of these predictors are in the equation, we're actually accounting for both of them. So the coefficients tell us what to change our expectation for y given a 1 unit change in either predictor while holding the other one fixed. Right? We're isolating the independent associations between this dependent variable and each of these independent variables. Of course, we could scale this up. We could have 20 or 30 or a million different predictors if we wanted to. Things can get crazy complicated, and at that point I can't show you a scatter plot because now we're moving into, nth dimensional space. But the idea is basically the same. We just add a dimension to a new column in our spreadsheet, and we can add a new predictor to our model. And now we're getting the unique or independent associations between each of these predictors and the outcome variable. That is very cool. And that is why regression is actually a workhorse in the social sciences and in science more broadly. It's an incredibly powerful tool.